Okay, so let's continue with our section on integration by substitution. On last class we saw the theory. Today it's all about examples, starting from the simplest one. And the first one is to integrate using a linear substitution. So by this point, if you remember the integration by substitution, look, the integration would be much easier if you had a variable of the form u equal to 2x plus 7. It's linear, precisely because you have a linear function that will do the transformation. If you compute du over dx, you have 2. So you actually have du equal to 2 dx, which means that dx is 1/2 of du. And if you plug this in, so you have the integral of the square root of 2x plus 7 dx is the integral. This would be u to the power 1/2. Then you have dx, which is 1/2 of du. So this goes out as a constant. So this is u 1/2 du times 1/2. And look, the procedure is clear now, or at least the motivation on why we did it. It is because now the integration is much easier with the variable u, which was just a linear transformation. Can people see? Or is there a visibility issue? Is everything okay? So look, we have this, right? So if I continue the integration, I have this is equal to 1/2. Then you do the integration over here, which is u to the 3/2 divided by 3/2 with the factor of 1/2 plus a constant. Do the multiplication, u to the 3/2 divided by 3 plus a constant c. And now you have to substitute back again for the function of x that you were dealing with. So this is u is equal to 2x plus 7 to the 3/2 divided by 3 plus a constant c. And this is the final result of the integration. Look, you can verify the computation. If this is actually the very first time you see integrals and integration by substitution, it might be difficult for you to understand why the method works, but given that you still are copying a little bit, I will give some intuition in the meantime. Look, at this point we have seen the integral just as the inverse operator of the derivative. There is actually another interpretation of the integral, which is the area under a curve. That happens when you have an integral over some given interval. So I'm just trying to make it easier for you to understand. Let's say that you have a function f of x defined over the interval a, b. And let's say, for sake of simplicity, that you divide this interval into, well, a mesh of a small increments delta x. And the midpoint in each one of these little intervals, say this is x1, x2, etc., etc. So the midpoint in this interval until you get to xn. So if you were actually to calculate something which is called the definite integral from the endpoint A to the endpoint B of this function by notation, dx, this is actually the sum from 1 to capital N, where n is the number of subintervals that you have. I'm just explaining it. This is actually not in the book in this chapter, so I'm just trying to make it easier for you to understand. I would prefer if you pay attention. Later on, if you want to copy, you can copy, but just pay attention to it, okay? So this is the sum of the function at these midpoint values. Let's say this would be xi times the delta x, which is constant for all of them, and I have n of this. Because what this is doing, it's basically just computing this area, right? So it would be this area, plus this area, plus this area, etc., etc. And it takes the value in the midpoint. So it's clear that it's approximately the area of the curve. Now, the integral is actually the limit as delta x approaches 0 of this stuff. that is actually the value of the integral when you have the endpoints from A to B. That is the area of the curve. I have not explained why, we have not seen it yet, but my point is that there is an actual reason the integral is related to a sum and the delta x come up for a reason. Because it is actually this little interval in the limit as it becomes smaller. So let's say that you do this approximation of the area under the curve, taking the values of the function and just approximating the area by the sum of the bars. When you make the delta x smaller, you will actually recover the value of the integral evaluated between A and B. I haven't explained exactly how, but it will be the case. Now, my point is that if you look at this linear function, let's say that you have 2 points, u1, 2x1 plus 7, u2, 2x2 plus 7, and you consider basically delta u, which is u2 minus u1. For the linear function, it actually holds that delta u is exactly 2 delta x, where delta x is equal to x2 minus x1. So, in the linear function, there is an intuitive geometrical concept of why that happens. I'm making a change of variables where I go from the space of x to the space of u, and if I keep track of the changes in u, I have to multiply by a factor of 2 for the changes in x. So there's some intuition, geometrical intuition behind this stuff. So it's not bizarre or without any intuition that we do this track of the change of variables from du to dx, because the du is approximately, basically when you are not having such a refined partition, approximately the delta u, and so you have to keep track of that when you do the change of variables. You cannot mix the variables x and u, but there is some intuition behind it. So my whole point is like, you can understand this as a set of rules to memorize. If it works for you, okay? But I'm trying to give some intuition of why we always have to keep track of this u prime. Because in the case where the functions are non-linear, that u prime factor will be precisely the transformation going from the x space to the u space. But in the linear functions, it is clear that that factor is 2 here. So there is some intuition, okay? So I'm just, look, it's very hard to give, this is not a pure math course. I understand that the aim is calculus for business, but I want to give my contribution to your intuition being a math person to you as a business person. So I'm just trying to make you understand. So now, in this case, it's clear why we keep track of this factor of 2. Here, we would have this because the function is linear. Now let's go to more complicated functions. We basically did the computation. I gave some intuition of how this works in the linear function. Keep this as the intuitive idea of why this will work for the case when we don't have linear transformations between x and u. So this example is done, okay? And the intuition is this. Now let's go to a new example where it's example 5.2.2, which is the integration by a quadratic substitution. And now, precisely, the problem is telling you that you won't use a linear transformation, but a quadratic one. And the problem is to find the integral of 8x times 4x squared minus 3 to the 5th power dx. Now, if you remember all our techniques, as we mentioned before, the most reasonable thing in this case would be to use u as the argument inside the 5th power. So u would be 4x squared minus 3. Moreover, the problem is actually pretty adequate for these baby steps, because if you think about it, the derivative of u with respect to x is 8x, which is exactly what we have on that other side, right? So we chose an easy problem. It's okay. We're learning, so that's fine. If you think about it now, u prime, which is du over dx, is equal to 8x. Okay? Now this transformation, or this rate, if you think about it, the derivative is the limit of the ratios between delta u and delta x. It's not constant. It depends on x. But given that I gave some intuition of why this du over dx is tracked, it's not so out of intuition if we simply say, well, du is equal to 8x times dx, precisely because of this, right? So now if I go back, I have all the elements to do the substitution. Here I will have my delta u, which is 8x times dx. here I would have basically u to the 5th power. And this would be du. So, if I do the substitution, this would be equal to u to the 5th power du. And now, with this change of variables, integration is actually pretty easy to perform, because this would be u to the 6th power divided by 6 plus a constant. The last part, of course, it's always to substitute back again the function that you proposed, which is u is equal to 4x squared minus 3 to the 6th power divided by 6 plus the constant of integration. Okay? But there's a reason I went into a lot of detail with the linear substitution, because in this case, when the substitution is quadratic, the derivative is taking the place of this ratio between the changes in x and the changes in u. It's not constant anymore. It's a function of x and it's 8x. However, if we have this interpretation that I'm going from the x space to the u space and keeping track of how delta u changes with delta x, the interpretation is clear. And now this is actually representing a sum, right? The sum of the function times the increment. That's why the integral is really this sum. When I go to the space in u, I have to keep track of the delta u, not the delta x, but I did that, so the integration is perfect. Okay? This is the intuition of why it works. I have not given at this point the concept of a definite integral, just indefinite integral, but I'm preparing you, because if you only memorize it as a set of rules, it will be harder for you to understand. So I'm trying to give this extra concept so that it at least makes some sense in intuition of why we do always this du in terms of dx. Okay? Is it a little bit like more intuitive for you after I did this explanation or not? A little? Okay. So look, today we basically do examples ad infinitum. So we did the second problem. Now the third problem is, you can keep copying, it's okay. So 5.2.3, it is using substitution on an exponential function. And the problem is now to find the integral. Keep an eye on what we are writing, because at some point, look, if this is the first time you read it, of course you have to do step by step. There will be one point in which you have so much experience where you will do the integrations by substitution just in your mind, without keeping track. So we're presenting baby examples for a reason, which is that they're simple enough that all the concepts are performed quickly. So if you have the integral of x cubed e exponential of x fourth plus 2 dx, again, it might simplify my life if I use as the variable, instead of x4 plus 2, a variable u, which is exactly the argument of the exponential, and very conveniently, actually, the derivative of x4 plus 2, except for some constant, is kind of already there, right? So let's substitute for the exponent, and let's do this step by step. Substitute for the exponent. So you have a variable u, which is equal to x4 plus 2. Let's say that you do again this procedure of du dx. The ratio is the derivative again. So du is equal to 4x cubed dx. So if you think about it, x cubed dx is equal to 1/4 of du. And it's making our life easier, right? Because, I mean, how convenient. We have x cubed dx, which is related to the du times a factor of 1/4. Now we do this, so x cubed e to the x4 plus 2 dx. If you want, let me group it in a way that it's intuitive for you, but it's like the middle of the work. It's e to the u, and then I have this factor x cubed dx, which is actually du over 4. So if I substitute, this is 1/4 of e to the u du, because the constant came out. And the exponential is actually the nicest thing to integrate, right? Because the derivative of the exponential is itself. So if you integrate, you get again the same function. So then you have 1/4 of e to the u plus a constant c, and you go back again to your substitution. So u was x to the 4th plus 2 divided by 4 plus c. Okay? But is it clear how the methodology worked? I had a problem simple enough where I was lucky enough to have also the derivative multiplying, except for one constant factor. I add, well, I did the algebra carefully to keep track of that factor. I substitute, it's a nice exponential function, which is pretty easy. I do the integration and then I substitute. And at the end I solve the problem. And if you want, you can verify by computing the derivative of what we get to see if we get the original sum, right? But it works. So, okay, we have done 3 examples where we have emphasized the idea of the intuition behind this integration by substitution. We'll continue with a new example. So, the next example is 5.2.4, which is related to using substitution and a rational function. So, now the problem is to find the integral of this function, x divided by x minus 1 dx. At this, yeah, sure. How much? This is good? Okay. So, again, I have told you that at some point in your mind you will do the substitutions kind of like automatically, right? I mean, you could do many things. You could add a plus and minus 1 in the numerator and make your life easier and so on. But formally speaking, if we are presenting integration by substitution in baby steps, step by step, let's do it one by one, okay? So the solution goes like this. And now I have to go back in this case. Substitute for the denominator, where you have a variable of the form u, which is x minus 1. Okay, this would be the first step. Now, for linear functions, life is easier, and actually this is basically x plus a constant. So it's even easier. So in this case, du is equal to dx. The derivative of this function is 1, so that's clear. And then if you actually do the change of variables, you would have that x is equal to u plus 1. Because we'll have to use it. So we could do it actually simpler, but I'm trying to do an all step-by-step case of this simple problem so that once and for all you see the procedure, and therefore more complicated examples you can do it on your own. Okay? So this is the integral of x divided by x minus 1 dx. So x was equal to u plus 1, x minus 1 was equal to u, du was equal to dx. So, this is very nice, and I'm actually pretty lucky because I can perform a division, right? So this would be 1 plus 1 over u du. Then I have the integration of a sum of the integrals. So here I would have u, and then I have plus the integral of 1 over u du. And what does this one look like? We have seen the rules before. It's like natural log of something, right? Remember? And so if you keep track of the rules that we learned before, this would be u plus natural log of absolute value of u plus a constant of integration. Now the final part is to substitute back again for the functions of x. So u was x minus 1, then you had natural log of absolute value of u, which is x minus 1, plus a constant c. And this is the result. I think it's good to do it step by step, especially if it's the first time that you see integrals and all these concepts. On the other hand, again, it could have been done simpler, which would be equivalent to this procedure, but just adding a plus and minus 1 in the numerator. So x plus 0, which is x minus 1 plus 1. You have a division, then you have 1 plus dx divided by x minus 1. And then on your mind, automatically, you know that dx is equal to d of x minus 1. So it goes okay, and it's exactly the same procedure as you. But I know it's the first time you see it, so I want you to do it step by step. So once you have done some examples, you do it on your mind. Okay? Okay, this was also some intuition behind of the linear functions and with a simple substitution. The next example is using substitution on a radical function where you have to find the integral of 3x plus 6 divided by square root of 2x squared plus 8x plus 3 dx. And again, all these examples are chosen for a reason, where you have actually the derivative very, you know, already the derivative of the function. So here, of course, the complicated stuff is inside the square root. So you have to substitute. Is there a question? So far, so good? Yeah, okay. You have to substitute for the argument inside the radical, so the square root thingy. So you define a variable u equal to 2x squared plus 8x plus 3. If you do the differentiation, you have the u equal to 4x plus 8 times the x, and we can actually do another simplification, which might be helpful, because this is 4 times x plus 2 dx. If you notice the object in the beginning, we have 3 times x plus 2 divided by square root. So everything is for a reason. There's always a purpose, right? 2x squared plus 8x plus 3 times the x. So I can take the factor of 3 out. Then basically this amounts to x plus 2 dx equal to 1/4 of the u. So I could actually multiply and divide by a 4, so I'm not doing any change. This is 4 times x plus 2 dx. So I'm keeping track of the same factors, everything is okay. And then I can simply express the radical in another form, 2x squared plus 8x plus 3 to the 1/2. Same thing. Now I do the substitution of all the variables that I have, which is 3/4 of the integral. Remember that this stuff was exactly the u, that's why I multiply and divide it by 4. Then I have u to the 1/2, and now it's actually I have made my life easier. This is 3/4 of u to the minus 1/2 du, because I have it in the denominator. So if I put it in the adequate power, this goes like that. Now I use my rules of integration, which is 3/4. Again, the power plus 1, so 1/2 divided by 1/2 to keep track. If you take the derivative of this is 1/2, so it nullifies with the denominator. Then 1/2 minus 1, so it's minus 1/2, which is what you have here. You keep track of these factors. Then you have the constant. Then you have 3u to the 1/2. 4 times 1/2 is 2, plus a constant c. Then you go back to the original function that you had. So this is 3, and then, okay, I can express also the 1/2 as a square root. Square root of 2x squared plus 8x plus 3 divided by 2 plus a constant c. Methodology is always the same, especially because we are dealing with simple examples where we have the function of something whose derivative is also on the other side. So the technique is like straightforward in this case. Find the adequate function, which was the argument of the radical. We notice that we have the derivative, keep track of the factors, do the integration of a simple function. Once we do it, substitute back again for the original expression in x, and we're done. And don't forget your constant of integration. So now that we have studied the technique in more detail, we'll do a new example where we will use substitution on a logarithmic function. So now, and again, these examples are chosen by design. So when I write the function, just keep track of what is the possible u, what is the derivative of that possible u, and then see if your guess makes sense, because at some point you will do this in your mind and you will do the guess on the spot. So here you have the integral of natural log of x squared divided by x dx. Now, well, you can recognize a couple stuff. Okay, this is the integral of natural log of x squared, 1 over x dx. And so this would be, if I would have u squared, where the u would be the natural log of x, and this is the u, because I have the derivative of natural log of x, which is 1 over x. So All what I'm trying to say is that you can notice that the derivative with respect to x of natural log of x is equal to 1 over x. So if you have u of the form natural log of x, du over dx is equal to 1 over x. So therefore du is equal to 1 over x dx. Okay? Again, I'm allowed to kind of like play with these du and dx because intuitively they are these delta x intervals when I subdivide indefinite interval. Okay? So now I have made my life easier because if I consider the original integral, natural log of x squared divided by x dx, this is the integral, well, I would have u squared, and then I have 1 over x dx, which is du, so this is du, which is easy to integrate. I have u cubed over 3 plus a constant of integration c. I plug in back again the function, so natural log of x cubed divided by 3 plus a constant c. But again, the methodology is the same. I'm lucky enough to have the function of a u, and then the derivative of that u with respect to x. I use all my machinery, step by step, and I substitute back again for the function. We're missing one last example, but these 7 examples presented today have the same technique because the problems are simple, and they're only focused on integration by substitution. So, the last example, well, there is, in addition to this last example, there is one example of why it doesn't work all the time, which is true. It's not the only method of integration, you have to use some other, but we will see. Is everything okay? Is there a question? Don't worry. Basically, in 3 lectures, we will see a method which is called integration by parts, which sometimes deals with the cases when this doesn't work. So, the next example is 5.2.7, which is basically use algebra before doing the substitution. Has everybody finished copying, or are you still on the other example? Okay. Is this okay? In the back? Okay. So, let's say you have to find the integral of x squared plus 3x plus 5 divided by x plus 1 dx. So you have the ratio of these 2 polynomials. Hopefully you can simplify a little bit the integrand by doing the division between polynomials. So basically you can notice that x squared plus 3x plus 5 is equal, so I will do the verification in 1 second, but let me write the result. It is equal to x plus 1 times x plus 2 plus 3. And now if we do the verification, it goes like this. So you have x plus 1 times x plus 2 plus 3 equal to x squared plus 3x plus 2 plus 3, which is equal to x squared plus 3x plus 5. I'm simplifying a little bit because if you look in the book, they actually do the division, but that will take us more time than what I want for something that you have already seen. So I want to focus on integration. So if I plug in this result, this one, let's say I have, okay, the integral of x squared plus 3x plus 5 divided by x plus 1 dx. Then plugging in the result, I have the integral of x plus 1 times x plus 2 plus 3 divided by x plus 1. So now you see why I did that division of polynomials. So now what I have is the integral of x plus 2 plus the quotient of 3 divided by x plus 1 dx. And, well, one of these integrals, or actually the first 2, are quite easy. The last one is you only have to do substitution, but it's very similar to the previous example. So here what you would have is equal to x squared divided by 2 plus 2x, and then plus the integral. And you could actually take out the 3 of dx divided by x plus 1. It's very similar to the previous example. The only difference is that, well, at least for part of the last example. So now you probably are having a guess of what we will use. So now we will use substitution for this last integral, where you define a variable which is u equal to x plus 1 to make our life simpler, where du is equal to dx, because it's a linear function, and u is equal to x plus 1, so basically the derivative is 1 in this case. So this would be equal to x squared over 2 plus 2x plus 3 divided by du divided by u. What does this look like? If you are studying for the exam, you should know. We already saw it in the previous slide. I mean, this is related to a log function. So here what you would have is x squared divided by 2 plus 2x plus 3. The integral of this stuff, I mean, this is equal, if you want, what we have is basically 1 over u derivative of, or du, sorry. Then this is 3 times natural log of absolute value of u plus a constant c. And the last step is to substitute back again for the function. So this is x squared divided by 2 plus 2x plus 3 natural log of absolute value of u, which is x plus 1. I close the absolute value, plus a constant of integration. And this is then the result. So we are hammering on this technique as much as we can to show how the methodology works. Of course, it's not... it doesn't work all the time, meaning that there are problems where you cannot amount to just do a simple integration by substitution. That's why there are many techniques of integration. We will see only a few in this course. Integration by parts is another one of those techniques. So we'll just present an example where you have to be more careful, okay? Sometimes you can use it, sometimes the problem is so complicated that you have to go to a different integration technique. So finally, we show that the method of substitution doesn't always work. With an example. So the example, of course, is chosen to be complicated enough so that it's not that easy to do it with just substitution. And it's basically, okay, the nickname, an integral, or example of an integral, where substitution fails. So the example is the following. You have the integral of x to the fourth e, where the power is x to the fourth plus 2 dx. Now, if in a nutshell you want me to tell you why it fails, is because in the other problem we had something proportional to the derivative of x to the fourth. In this case, we don't have it, right? In the previous problem, we had x cubed, because if you take the derivative of x fourth plus 2, you have 4 times x cubed. In this case, we have x to the fourth. So there is still one factor of x that we have to realize how we're going to deal with, and that is the thing that causes the issue. That's pretty much the summary. Now, let's try to do it to see why it doesn't work. The first approach, the naive approach, would be to take u equal to x to the fourth power plus 2, where you have the u equal for x cubed dx. Now, moreover, if you do actually the substitution for x, pass the 2 to the other side, take the fourth root. So 1, well, actually, yeah, I don't want to express it in this way. Not with the radicals. So u minus 2 to the power 1/4. So if I keep track of this, this is equal, well, I could make my life easier. So this is equal to x times e x to the fourth plus 2 times a factor x cubed dx, which is not chosen accidentally. It is because if I keep track of this, this is equal to x, then e to the u, then this is equal to du over 4. But now I plug in back to have everything in terms of u. This would be equal to u minus 2 to the 1/4 times e to the u du. And if you want to, let's keep the factor of 4 over here. But it's clear, right? I mean, before where I have x cubed, it was easier, this factor did not appear. In this case, it doesn't seem that our life has been made easier, because we still have this stuff. So it doesn't reduce to one of the simple rules of integration that we presented in section 5.1. Of course, you have to use another kind of method. There is something called integration by parts that would be useful to actually deal with this integral. So wait for it 1 week and then we will study it, okay? But what I'm trying to present it as is not so simple. I mean, this would be equal to 1/4 of the integral of the 4th root u minus 2 e to the u du. And frankly, if you make a comparison between this function and the original function, it doesn't look that we have simplified our life. So, okay, just a note, doesn't look simpler than the original. So the moral of this story is that substitution fails in this case, and we have to look for other methods. Okay? So sometimes you can use it, sometimes the integrand is so complicated that you have to resort to other techniques. That is the moral of the story. So, okay, we have done 7 examples. Is the technique at least kind of understood into what you have to do if you're faced with an exercise of integration by substitution? Okay. So, try to study the examples in your own house. Try to do some others. It's the only way. Look, this is a very short calculus course. They are different. If you see, actually you have 4 courses. And there are courses where you devote a month to integration. This is not the case. In those kind of courses, you study so many integration techniques that you're prepared for many of them. Not everything is integrable. There are actually some functions which are very complicated and there is no analytic solution for them. There is something called elliptic integrals. My point is, we are just studying the basics. So, these 7 examples have tried to present the technique, plus 1 example that didn't work. And now, has everybody finished copying, or do you still need some time? Okay. So, we will go to applications where we use the method of substitution, and there is one small comment regarding this kind of problem. So, before I present the next example, we have to define what is the concept of the differential equation. And so, we will mention briefly what is a differential equation, and then we will do examples of differential equations or DFQs where we use substitution. So a DFQ for shortness is an equation involving derivatives of functions. Now, the best way to learn what it is to do an example. So the example, which is not in this section of the book, but I will do it anyways, is to find the function f such that f prime equal to k f of x. Let's say, without having taught you how to solve a DFQ, somebody asks you that question. Find a function such that the derivative is equal to k times the original function. Which candidate would you propose? Make k equal to 1. Which candidate would you propose? The exponential, right? If k was equal to 1, the derivative of the exponential is the exponential itself. Now, I have a little constant k here. What could I do? I could add a constant kx, exponential of kx, and when you take the derivative, the k constant comes down. I'm just trying to say that you know the material for which you could be able to solve this. Now I'm going to do the solution, okay? So, the integration goes like this. You have f prime over f equal to k. So far, so good, right? I pass to the other side. Now I do the integration. That implies that the integral of f prime over f, well, the x is equal to integral of k dx. Now, this looks like the example of the natural log thingy, right? So, well, on one hand, this is equal to kx plus a constant of integration c. On the other, if I perform this stuff, this is actually the integral of the derivative with respect to x of natural log of a function of x dx. Now, life is solved, right? The integral and the derivative are inverse operators, so I will have natural log of f of x. It's equal to this. So you're seeing that we are going to get to that solution. In fact, look, if you want me to be super formal, I could put the absolute value, fair enough. Let's say that I basically take the exponential, so e to the kx plus c is equal to absolute value of f of x. Notice that this is equal to e to the kx times e to the c, where both these two are positive. So this is absolute value, so when I take actually f of x, this is equal to plus minus e to the c times e to the kx. And if I define a constant a, which is plus minus e to the c, now this constant can be positive or negative. I have that the actual solution is equal to a times e to the kx. So which is exactly, whoa, sorry, I didn't realize that it wasn't focusing. But this is the formal way that you would solve the DFQ for this simple problem. So there's a reason we have been studying like these exponential functions. Now you're familiar enough with the derivative so that you can recognize the method to solve it. So this is, formally speaking, what we did is basically, okay, if we had something like y equal to f of x, at this point, what we did was to separate the variables, the y's on one side, the x on the others. So the method used for this is method of separation of variables. Now, it seems unrelated to what we saw regarding integration by substitution, but it's not. Because, look, there are full courses in differential equations, okay? So this is just a little baby introduction to the topic. The point is that also in the first course of DFQs, you would see methods for solving that. And those are very related to integration, and you can use the integration by substitution to solve some kinds of DFQs. That is the connection with this topic. Okay? So now we will present, and well, okay, so there's a couple things to say. This is basically the general solution. This is the name for this. And then later on we will explain what is an initial value problem, which has some intuition from physics, which is when you add an initial condition, but we have to go step by step. So now we deal with, I will say DFQs for simplicity. There is also another name, which is called ODE. So we will study a DFQ that involves substitution method. And it is example 5.2.9, which is using substitution to solve a separable, you will see why it's separable, DFQ. The command of the exercise is to find the general solution, so something like this fashion, of the separable. Let me define separable in a second. Well, actually we did an example related to it. DFQ of the form dy over dx equal to the division of the square root of 4 minus y squared divided by xy. Now, why is this called separable? It's because essentially multiplying and dividing, you can put all the variables y on one side and all the variables x on the other side. That is just the notation, okay? So if we go for the solution, first separate the variables. Means, okay, just to give you some intuition, y on one side, x on the other of the equation. So, okay, again, look, I'm in a world where I'm allowed to play with these dy and dx as if they were actually factors. Formally speaking, that is not true because the derivative is a limit. There is actually a whole calculus invented so that you can do that stuff. And that is called the calculus of the infinitesimal. That is for a pure mathematician. You do not have to see it here, okay? But there is some intuition behind it, which is what I try to present with this picture of the graph. And formally speaking, it is justified. Now, if you play with the variables, let's say you pass the y, dy, and then you have equal, well, you have to divide by 4 minus y squared to put everything in y on the other side, and then you have the dx divided by x. Okay, so I pass this one here, this over here, this dx over here. Formally speaking, it's the same thing. Now, I would have to integrate because you have an equality, so it holds also for integration. Now, it's clear why I did that, because when I pass all the stuff related to y on one side and all the stuff related to x on the other side, I can do the integration and my life is much easier. So the first one is easy because this is the natural log of absolute value of x plus c. So you have seen this rule before. This is the integral of dx over x. Now for the second one, this is where you have to use substitution. So in this case, again, the technique. Just remember what we saw in the first half of the class. U is equal to 4 minus y squared. If you have this, then du is equal to minus 2y dy. So that means that y dy is equal to minus 1/2 of the u. And it is clear why I'm writing all this stuff, because I have y dy in the numerator, and then I have the radical of u. So just to finish our computation, the integral of y dy divided by the square root of 4 minus y squared is equal, and then I plug in this stuff, so this is minus 1/2 integral of the u, and then I have u to the 1/2, because u is this. So, and you have the radical, so that is a 1/2 power. So now my life is much easier. This is minus 1/2 of the integral of u minus 1/2 du. Then I do the computation with the first formulas that we saw in the section 5.1. This is u to the 1/2 divided by 1/2. Do the computation, 1/2 multiplies, eliminates this stuff. Then we'll have minus 1 is equal to minus 1/2 times the factor. So this is equal to, in your mind you will do it eventually just automatically. For the moment this is an introductory presentation of the topic. So this is minus u to the 1/2. And now I go back to what I had, right? So what I have is that u, well, minus u to the 1/2 is equal to this stuff, which is natural log of absolute value of x plus c. But I did a substitution, which I still have to finish. So if I plug it in here, this is minus, and then the radical, because I have the 1/2 as a power, of 4 minus y squared. Okay? If you want, okay, minus 4 minus y squared to the 1/2. It's the same. The point is that the solution to the problem is up to here. It's just a different way to present the solution, which is called, well, I mean, you could solve, well, basically, okay, square, pass the 4, etc., and you have y as a function of x. This has a name. This is just the implicit form. This is actually, look, when you study differential equations, if you ever take a course on DFQs, sometimes it's harder to do the expression of y in terms of x. In this case, perhaps it is not that hard, but the point is that the same way you have functions, y as a function of x, you have curves in a plane, where you have a set of points of x and y that satisfy the problem, which is this case. So, well, I will do the posing of a problem at the end, and then we will continue next class. So let me write the problem, and then we start from there in next class. So in the next class, we will do the example 5.2.10, which is to obtain the price from its rate of change. So you have the price, which is denoted by the variable P, which is in dollars per unit. And you're given the rate of change, which is dp dx equal to minus 135x divided by the square root of 9 plus x squared. Now, x is expressed in 100 units, and x denotes something called the consumer demand, which is the number of units purchased at that price. So, suppose 400 units, and so you have to be mindful of the units because x is expressed in hundreds of units, so that means that x is equal to 4, are demanded when the price is equal to 30. So the first command is to find the demand function p of x. Okay? So we start from here next class. Keep it in mind because I won't write this again.